Okay, so time for our integration recap. It's going to be pretty quick, so if you're feeling hazy about your integration, please just spend some time going through it and mostly spend time doing examples, because just like with differentiation, it's really all about practice. I can tell you stuff, but unless you actually just spend time working with the concepts, it ain't going to happen. So why might you want to devote some time to integration? Well, a lot of the principles of science, no matter which area of science you look at, whether it's ecology or physics or chemistry, these principles are talked about in terms of rates of change. And we've seen that mathematically, a rate of change is expressed as a derivative. So it shouldn't come as a huge surprise that when you're modeling physical phenomena, you often end up with equations that have derivatives in them. And while that initially is quite a good thing, ultimately we want to end up with functions that describe our systems when the functions don't have derivatives. So we need some way of finding out the function when all we know about is the derivative. And that's really what integration is all about. Now, you've actually seen examples of these already. For example, in physics, you will have seen this equation over here, which links the distance traveled to the time and the initial velocity, and also the acceleration. And of course, remember that our acceleration is just the second derivative with respect to time of our displacement. So really, if you were to write this equation out in kind of mathematical detail, this is what you'd have. And you'll notice you've got an equation and it's got derivatives in it. We've also in the tutorial been looking at this equation over here, which when we talk about things like population growth or an epidemic and how infection rates spread, this says, well, the rate of change of the number of infections, for example, or the rate of change of the population is equal to some constant times the current population or the current number of infections. So again, we've got an equation that has a derivative in it. But ultimately what we would like to have is some function n of t, which is equal to, and it just has things involving t. It doesn't have any derivatives. So that's what we're going to start looking at for the rest of this lecture. So if we're solving an equation that includes derivatives, then really what we're thinking is we want to find a function which satisfies or solves the equation. What does it mean for a function to satisfy or solve an equation? Well, it means that if we substitute the function itself into the left-hand side of the equation, and then we substitute into the right-hand side of the equation, and we take whatever derivatives we need to, wherever they are, then we should end up with a left-hand side that equals a right-hand side. What am I talking about here? Well, suppose that we think that this n of t equal to e to the kt is a solution to this equation. So we're saying, suppose that this n of t, which is equal to e to the kt, satisfies that equation. Well, let's look at the right-hand side and the left-hand side when we substitute that particular n of t in. So if we look at the left-hand side, we get dn of t by dt is going to be d by dt of this bunny over here, e to the kt, and we know that if we take the derivative of e to the kt with respect to t, we're going to end up with k e to the kt. All right, and if we look at the right-hand side, what do we get? Well, we've got k n of t, and I'm going to again substitute in the actual function that I'm using here, so that's going to be k e to the kt, and with joy and delight we see that our left-hand side and our right-hand side are equal, so we know that this particular function satisfies the equation. Now I should point out that just because you found one equation doesn't mean it's the only one. There are loads, in fact there are infinitely many functions that would satisfy this equation. So you can check for yourself that you could, for example, try n of t equal to 6 e to the kt. And that will also satisfy that equation. You could try this one, which is, let's try e to the kt plus 2 Does that satisfy the equation? Well, let's have a quick check. If we look at the left-hand side, we've got d by dt of e to the kt plus 2. If we take that derivative, that's going to be k e to the kt. And if we look at the right-hand side, then we've got k times n of t, which is equal to k times e to the kt plus 2. And now you'll see that there are some things that don't fit. So since our left-hand side and right-hand side don't match, this is not a solution. Okay, but if you check, you'll find that that one is a solution. And you can guess that pretty much for any constant that you put in over there, you're going to get a solution. Okay, so you've seen an example of one that does work and one that doesn't work. So what we're trying to do when we integrate is find all the functions which satisfy the differential equation. So I'm calling it a differential equation because it's got derivatives in it. So we're really trying to find, somehow we need to undo the differentiation that's implied in the equation. And there are plenty of different techniques for this, and they all depend on the particular form of the equation that you're trying to deal with. So we're going to start out with the simplest, which is anti-differentiation. As is clear by the name, it's about undoing. So it's anti-differentiation. You're going in the opposite direction to differentiation. And sometimes you'll also hear this referred to as indefinite integration. And once we see where it goes, I'll explain why it's called indefinite. So this technique is mostly useful when you've got a single explicit derivative in the equation. So situations like dy by dx is equal to 2x. So here you know that your derivative is an explicit function of the independent variable x. Similarly over here we have a second derivative, but that doesn't matter. Our second derivative is an explicit function of the independent variable x. So those are the kinds of things that we're dealing with. Okay, so just some terminology. If we have two functions, little g and big G, such that the derivative of big G is little g, then we call big G an antiderivative. Now here's where you need to kind of keep your wits about you. When we talked about derivatives, we could say if we had some function, we could find the derivative. There was only one. But in fact, as we've seen, there are many antiderivatives. So here's the important thing to remember. If there's at least one function g, so one function little g, such that big G's derivative is equal to that little g, then it turns out actually there are infinitely many. And we'll see why in a moment. Okay, so just a word about notation. So to indicate that we want to find the antiderivative family, so I'm calling it a family because there are infinitely many of them. So if we want to find the antiderivative family of little g, then we write this funny thing here, which is like a weird s. It comes from sum, because originally, and we'll see a little bit later what I'm talking about, integrals were thought of as sums of things. So this funny thing here says, take the integral, the indefinite integral of little g of x, and then finishing off over here, we've got with respect to x. So this is a lot like the notation that we have for the derivative, which would say something like, take the derivative with respect to x of f of x. Whoops. Okay, so the important thing here is you really need to have both these bits of information, which this bit says take the derivative, and this bit says with respect to x. And at the moment, you might think, well, obviously it's with respect to x. What else could it be? But spoiler alert, you can actually have more variables, and then you kind of need to specify which one you're going to be using. So get into the habit now. Okay, so if big G of x is any antiderivative of little g of x, so remember an antiderivative says if I take the derivative of this big G, I'm going to end up with this little g, then in fact this indefinite integral of little g is big G of x plus some constant, where c is a real constant. And that's where the whole family thing comes in, because c can be anything. So big G of x plus any constant is going to give you an indefinite integral of big G of x. So we think of the indefinite integral as the whole family, all of them. Okay. So how do we find this big G of x? Because remember, we want to try and find this thing, which when we take the derivative gives us the thing that we're starting off with. Okay, well, like a lot of things in maths, one of the first things you can do is make an educated guess. Then we have some basic rules. If you remember, you had basic rules for differentiation, or we've got some for integration, and they're basically the same. Then we have integration by substitution, and that's really when you're undoing the chain rule. So we're always thinking that the thing we're trying to work with is the derivative of something, and if the thing that you found was the derivative that used the chain rule, integration by substitution will help you find the original thing. Another option is integration by parts, and that's where we're really undoing the product rule. So keeping those in mind can help you spot which technique to use. And of course, nowadays, well, actually, frankly, if you were going to be doing most integration out in the world, you'd pretty much use a computer. But for this course, it's going to be helpful to actually be able to do some of this stuff by hand. So don't just plug it into your calculator. Actually, make sure you can do this. All right, so let's do some practice. So we want to find the antiderivative of e to the x, or the indefinite integral of e to the x. So what do you have to differentiate in order to get e to the x? Well, we know that if you differentiate e to the x, you just get e to the x. So it must be, that's an antiderivative. But remember, we have to add plus c, because notice if I differentiate, for example, e to the x plus 2, what will I get? I will get e to the x. On the other hand, if I differentiate d by dx e to the x minus pi, I will also get e to the x. So any form of a function e to the x plus some constant is going to give me something which, when I take the derivative, gives me this e to the x. Okay. How about 2 times x? What did I have to differentiate in order to get 2 times x? Well, hopefully you're thinking, power rule maybe? So if I differentiate x squared, then I will get 2x. And then I need my plus c, because again, if I differentiate anything x squared plus some constant, I'm going to end up with 2x. Okay, what did I have to differentiate in order to get just x? So here you can say, well, okay, I got 2x when I differentiated x squared. So presumably if I divided x squared by 2, then when I bring the 2 down when I differentiate, it's going to go away. So the answer must be a half x squared plus c. Okay, and you can always just check this. So if I take the derivative of that, d by dx of half x squared plus c, derivative of a half x squared, that's going to be a half times 2x, that's, yeah, there we go. X, and the derivative of the plus c is 0. Okay, nice. Derivative, so what did I have to differentiate in order to get sine of x? Well, you know, if we differentiate cosine, we get minus sine. So if I differentiate minus cosine, I will get minus sine, which is sine. So I'm going to have minus cosine of x plus c. Okay, so far so good. We are rocketing along, finding indefinite integrals, but obviously it gets more complicated. Okay, so as you might expect, we have some basic rules, and they really are the kind of reciprocal of the differentiation basic rules that you learned. So for example, if we have a look over here, if we want to integrate a constant, we're going to end up with that constant times x plus c. I wouldn't worry too much about those two rules, because there are special cases of this rule which kind of undoes the product rule, the power rule for differentiation. So if you want to integrate x to the p, then what you need to do is you need to take your integral is going to be x to the p plus 1 divided by p plus 1. And you can check that if you differentiate that, you end up back with x to the p. And don't forget your plus c. So this one might look a little bit strange. So we know that if we differentiate the natural log of x, then we're going to get 1 over x. So why is it that if we integrate 1 over x, we end up with the natural log of absolute value of x? And I'm going to leave you to think about that. But the trick is really that we're thinking, when we write this here, we're writing this as the integral of, 1 over x with respect to x. Remember that we could put any x that we like in here. We could put a negative in. But we're not allowed to put negative x's into the natural log because it's not defined for negative x's. So in order to deal with that issue, we put an absolute value around the solution, in our solution, to ensure that the thing that we're putting inside the natural log is positive, so that the universe doesn't explode or something. Okay, so just be a little bit aware of that one. Okay. And then finally, we know that the derivative of e to the x is just e to the x, so the integral is going to be e to the x. Here's how we deal with base b rather than base e, as you might expect. And you've got sine of x and cosine of x. And I wouldn't really worry about tan of x for this course, but in case you need it one day, there it is. So these are the ones that you need to know. And you can always remember them by thinking about the going differentiation in the other direction. All right, so let's quickly do some practice. So I suggest that you pause the video and give this a try, and then come back and we'll go through them. All right, here we go. So we want to find the following. We want to find the indefinite integral of cos of 3x plus 4x squared with respect to x. Okay, so what did I have to differentiate in order to get cosine of 3x? Well, I know that it's going to be something like sine of 3x, but if I differentiate sine of 3x, there's a chain rule involved there, and I'll get a 3 coming out. So I'm going to need to multiply this by 1/3. Okay, how about, what did I have to differentiate to get 4x squared? Well, I had to differentiate x cubed times something, and when I took that derivative, I would have had a 3 coming down, so I'm going to have to divide by 3, and then I'm going to need a 4 to take care of that constant there. And then I mustn't forget plus c. So there we go. If I differentiate that bunny, I hope that I'll get this thing over here. You better double check. It's a bit late this evening, so if I'm making mistakes, just let me know. Okay, so what did I have to differentiate in order to get 6e to the 4x? I know that the derivative of e to the x is just e to the x, but this is e to the 4x. So if I'd taken the derivative of e to the 4x, I would have got a 4 that came along. So I'm going to need to divide through by 4 and then multiply by 6 to get that 6 and add my constant. Okay, I seem to have gotten all my dx's here. What did I have to differentiate in order to get 2 over x? Well, we know that if we integrate 1 over x, we get the natural log of the absolute value of x. But this is actually 2 times that, so I must have a 2 there and add my constant. Yay! Okay, what did I have to differentiate in order to get 2 over x squared? Well, I'm going to rewrite this slightly as 2x to the minus 2 dx. And now I see that it's a power rule. So I must have started out with an x to the minus 1, because when I differentiate that, it's going to bring down a minus, so I'm going to need to have a divide by a minus, which is the same as timesing by a minus, and I'm going to need a 2 over there, plus c. So the thing to notice here is this rule here, read the fine print, only applies when p is not equal to 1, because when p is equal to 1, I mean p is, this should be p is equal to minus 1, because when p is equal to minus 1, we're actually in this case over here. Okay, so just be a little bit careful. Okay, so that's all the basic cases. But now we have to deal with slightly more complicated things. For example, suppose what we're handed is a derivative that comes from taking the chain rule of a function. Well, just to remind you of what the chain rule says, it says that if g is differentiable and f is also differentiable at g of x, then the composite function, f composed of g of x, is differentiable at x, and it's given by the derivative of f at g of x times the derivative of g of x. Okay, so if we go in the opposite direction, what we must have is that our composition is equal to this composition here. So the derivative of our composition is equal to, when we integrate, this composition here. So the question is, how do we do that? And the trick is that we make the substitution u is equal to g of x. So this is going to be a lot more straightforward if I just show some examples. All right, so let's have a look at this first one over here. And we probably need another page. Okay, so here we go. So think about what we're doing here. We're wanting to express this thing as the somewhat convoluted f prime of g of x times the derivative of g of x. But you'll notice, if you have a look at this, that we can clearly see, so, okay, before we go there, the thing to notice is that we've got an f evaluated at g of x, and we've got a derivative of g of x. So the trick is to have a look and see if you can find both some function and its derivative, and that function is probably going to be your g of x. So if we have a look at this bunny over here, notice that we've got an x cubed in the denominator and an x squared in the numerator. So this is a hint that there's a good chance that this denominator with some factor is going to be our g of x, because this, our numerator, could very well be the derivative of that, the g prime of x, ignoring factors, constant factors. So let's see how this works. So I'm going to take a guess and say, let u of x equal 5x cubed plus 1. Okay, good so far. Then du by dx is equal to, so I'm going to take the derivative. So this is just, I'm really working with g here as far as I'm concerned. I'm going to take the derivative, and that's going to give me 15x squared. How does this help me? Well, what I'm really wanting to do is change my variables. So I want to change from using x's to using u's, because that's going to make my life a lot easier. Because notice that my u is just a u, whereas 5x cubed plus 1 is a bit more complicated. So what I need to do is I need to be able to replace all the x's in here with things involving u, including I'm going to need to have, somehow I'm going to need to turn this magically into a du. Well, let's see what happens. So one way to do this is to say, well, at the moment, let's see what we've got. I can certainly replace the denominator with a u, because my 5x cubed plus 1 is my denominator. And then here, up top, I have an x squared times dx. But what I really want is, so I've got an x squared here, I've got this annoying 15, and I would like it to be multiplied by dx. And this is where things get a little hand wavy. And we're going to treat this du by dx as a fraction. It's not a fraction, it's a derivative. But for the purposes of this, this works. So I'm going to multiply both sides by dx. If you want the proper reason for this, go in and do a serious course in calculus. But this works, okay? So I've got du is 15x squared dx. Almost what we want. We don't want that 15, so let's divide through by 15. So I've got 1 over 15 du is equal to, whoops, x squared dx. So now I'm going to replace this x squared dx with 1 over 15 du. Okay, so I've got 1 over 15 and I've got a du. So notice what we've done. By making this cunning substitution, we've taken this complicated thing and we've turned it into this pretty straightforward thing. Because we absolutely know how to integrate 1 over u. We know what that is. And we've just got this 1 over 15, which is coming along for the right. So if we find the antiderivative here, it's going to be 1 over 15 natural log of the absolute value of u plus c. We're not quite home and dry because our original function was in terms of x. So now we just go back and replace our u's with x's. So we've got 1 over 15 natural log of the absolute value of 5x cubed plus 1 plus c. Okay, if this is the first time that you're seeing this, I'm sure that it's probably a bit like, what the hell? Watch it again slowly, try it for yourself. Everyone finds their own way of doing this. This is the way I was taught when I was in first year, but I've seen lots of alternatives. So if it's not working for you, maybe do a Google search, chat to your friends, see if you can figure this one out. But let's look at another example. So here we've got b. So again, if you have a look at this, you'll see that this has the kind of the hinty type of form, which says, okay, I've got an outer function of sine of x, I've got an inner function of e to the x, and if I think about what must have happened, I took the derivative of some outer function, and then I had to multiply it by the derivative of the inner function, and since the derivative of e to the x is e to the x, that's what's happening here. So it was a bit of a quick explanation, but the idea here is I see this e to the x inside the sign and this e to the x outside of the sign, and I think, okay, I've got the derivative of e to the x over here from this e to the x. So let's see how this works out. So I'm going to pick as my u e to the x. If I take the derivative, then I end up with e to the x again. Now I do the somewhat illegal multiplying both sides by dx to give me du is equal to e to the x dx. And now what I want to do is I want to replace everything involving x's into things with things involving u's. So I'm going to have the integral. Now sine of e to the x is going to become sine of u. And then notice that this e to the x times dx is this thing here, which is just du. So that was pretty nice. because now I'm just integrating sine of u, which we know how to do. That's going to be minus cosine of u plus c. And again, our original question was in x's, so we need to just remember to plug in for whatever u is equal to, which in this case was e to the x. And you can double check, if you differentiate this bunny over here, you will end up with e to the x sine e to the x. Okay, maybe we need one more example. So we've got c over here. So again, we have a look and we see, okay, inside my cosine of x, I've got this root x. And if I look outside, it's tempting to say, but I've got a root x, and the derivative of root x is not root x. But remember that the derivative of x to the half is a half x to the minus a half, which we could also write as a half 1 over x to the half. So if we take the derivative of root x, what we end up with is 1 over root x. So that gives us the hint that what we should be taking as our u is going to be our x to the half, or our root x. I just find it easier working with half. If we take our derivative, we've got du by dx is going to be equal to a half x to the minus a half. We do the multiplying through by dx thing. We get du is equal to half x to the minus a half dx. And now we start thinking about how are we going to do this substitution thing. Well, we're going to have the cos of root x, and we're declaring that root x is u, so we've got the cosine of u. And now remember, what we've really got here is 1 over root x times dx. But if we take du, at the moment that's equal to a half times 1 over root x dx. So what we need to do is multiply through by 2, and this will give us 2 du is equal to 1 over root x dx. So we can replace this 1 over root x dx with 2 du. So let's do that. So I've got a 2 du, and that's a very delightful and easy thing to integrate. We've got to have 2 sine of u plus c. And then finally doing our substitution back, we've got 2 sine of root x plus c. Done and dusted. So again, you can double check, make sure if you differentiate this thing over here, you will end up with this thing over here. Okay. Next topic. So we've just dealt with how we kind of undo the chain rule. Now we're thinking about what happens if we want to undo integration by parts. So just to remind you, sorry, integration by parts is undoing the product rule, sorry. Okay, so our product rule, if we've got some function p of x which consists of an f times a g, then the derivative of that product is whichever way around you prefer doing it. Write down the first function, take the derivative of the second, and add to that, writing down the second, take the derivative of the first. Okay, so how do we use this? Well, let's start by looking in this form over here. What we're really going to do is we're going to do a kind of a switcheroo. So we're imagining that we're reorganizing this thing so that we have this term on the left, f of x, g prime of x, and on the right we've got our p prime of x minus g of x f prime of x. Okay? And then what we're going to do is we're going to integrate both sides. So we're going to integrate this side, and we're going to integrate this side over here, so that gives us that and that. But the key thing to notice is that this bunny over here is asking us, what did we have to differentiate in order to get the derivative of big P? But what we had to differentiate in order to get the derivative of big P was this. So we end up with saying the integral of f of x times the derivative of g of x dx must be equal to f of x times g of x minus the integral of g of x times f prime of x. So really what this technique does for us is it gives us a way of taking a product of terms that we might not be able to integrate and rewriting this in a form of something that we can integrate. So that's the simplest way to think about it. The way that you might have learnt it is this way. If that's the terminology that you use, that's fine. I am mostly going to focus on using this form over here. Okay, so let's have a look at an example. So the first thing that you should do if you see a function inside an integral that looks like a product of two things, so here we've got a t times an e to the minus t, is ask if you can solve by substitution, which we did previously, because that's probably going to be your easiest bet. But if you have a look here, substitution requires that we have some function that's been put in combination with another one, and here we've got e which has minus t inside it, but if we take the derivative of minus t, we're not going to end up with t, we're going to get minus 1. So substitution isn't going to work here. So the next thing to try is the product rule, or undoing the product rule, which is this bit over here. Integration by parts. So let's just make a note of what the rule says. So basically when you're trying to integrate by parts, you have a something times a something else, and you're going to assign one of those to be your f of x, and that's going to be the thing that you take the derivative of. And then you're going to assign the other thing to be the derivative of g, and that's the thing that you're going to have to integrate. So the trick is always to pick your g first. So the thing that you're going to have to integrate needs to be something that you know how to integrate. In this case, we can integrate both of them, so the idea is to keep it simple. So it's easier to integrate e to the minus t than it is to integrate t, because t involves squaring stuff and things like that. So let me show you how it works. So I'm going to pick as my f of x, or rather my f of t, because we're actually working with t's here. My f of t is going to be equal to t, and the thing that I'm going to end up integrating, my g of t, is going to be e to the minus t. So that's my g prime of t. Okay? And now you'll see that in my solution over here, I need f of x, I need g of x, or g of t, and I'm going to need my g of t, and I'm going to need the derivative. So I take the derivative of my f of t with respect to t. Derivative of t is just 1. And I'm going to integrate my derivative of g. So I need to integrate this bunny over here. So my g of t is going to be equal to minus e to the minus t. Now technically I should have a plus c, but it's going to turn out that we don't need it because we're going to add the plus c at the end. At the moment all we need here is any particular antiderivative. So I'm not going to use the plus c here. I'm just going to let my g of t be equal to minus e to the minus t. How does this help? Well, now we can rewrite this integral, which we didn't know how to do, as something that we do know how to do. So we need our f times our g. So I'm going to have minus t e to the minus t minus, and now I'm going to have to take the integral of g of x. So that's, I'm going to have a plus there, e to the minus t times the derivative of f, which in this case is just 1. So we've just made life a lot easier. I couldn't solve this, but I can totally integrate that. So let's go ahead and do that. So we've got a minus t e to the minus t plus, well, in fact, it ends up being a minus again because I'm integrating e to the minus t. So this is going to be e to the minus t. And now finally, I have my plus c. So you could check that if I'd used the plus c over here and I'd carried that all the way through, I could redefine the constants. I'd have a whole bunch of constants. I could add them all together and just define them as a new constant. So for this, it's fine to just write like this. Do yourself a favor and check that if you differentiate this thing over here, you get that t e to the minus t there. Okay, so let's check with another example. So these two are quite straightforward, but I'm going to, and I'll put the solutions in the final version of this, but let's have a look at D. Okay, so have a look and see. Now, it might be tempting to say, I could use substitution here because I've got an x squared and I've got an x. And x is kind of like the derivative of x squared, barring some constant. But in fact, I can't, because what you want is, you would have wanted the x squared inside the sign, because you want to have a function within another function if you're going to use substitution. So you could try it, but it wouldn't work. So the next thing you obviously think about is, okay, maybe we can do integration by parts. So we need to pick what's going to be our f of x, and what's going to be, so the thing that we take the derivative of, and what's going to be the thing that we integrate. Now, from my perspective, I would rather take the derivative of x squared and integrate sine of x. It just seems to work simpler that way. You could try it going the other way and you'd find that you end up, if you're integrating x squared, you'd end up with an x cubed, which you'd then have to integrate again. We don't want that. So hopefully by taking the derivative of x squared, we're going to make things simpler. Let's see what happens. So I'm going to make f of x by x squared, and I'm going to make the thing I'm going to integrate my sine of x. Okay, so take the derivative. I've got my f of x is equal to 2x. The derivative is 2x. Integrating, I'm going to get minus cosine of x, and I should have a plus c, but I'm going to remember to put my plus c right at the end. Okay, so what happens if I write this all out? So I've got to have f times g, so that's going to be a minus x squared cosine of x minus, and let's just remind ourselves, g of x times, so I'm going to have those two multiplied together. So I've got a minus times a minus, so that's a plus, 2 times x cos x dx. And at this point you might feel slightly annoyed because notice this isn't something that we can just integrate simply. And so sometimes what happens is you need to use substitution twice. So we're going to do the same trick again. We're going to integrate x cos x dx using substitution. Because, we have to use parts twice. We can't use substitution here. You can check it. Okay, so again we need to pick what we're going to let our f of x be, what we're going to let our g prime of x be. And notice we managed to reduce the power of x. So if we make that the thing we take the derivative of again, we're going to end up with a 1, which sounds like it might be useful. So let's make that our x. So if we take that derivative, it's going to be equal to 1. We can easily integrate cosine of x. So we're going to let our g of x be sine of x plus c, but we're going to include our constants later. All right, so this integral here, x cosine of x dx, is going to be equal to, so we've got f of x times g of x, so that's x sine of x minus the integral of f prime of x times g of x, so minus the integral of sine of x dx. And now you see, yay, we've got something we can integrate simply, so we've got it's equal to x sine of x minus, whoops, and we're actually integrating this, so we get cosine of x plus c. And so finally, because this was all just to work out this bunny over here, let's plug that all back in. So finally we have our x squared sine of x dx is equal to minus x squared cosine of x plus 2 times this thing over here, x sine of x minus cosine of x plus c. And if we tidy this all up, we're going to get minus x squared cosine of x plus 2x sine of x minus 2 cosine of x. And I'm going to have, we would have plus 2c, and I'm just going to define a new constant called d, which is equal to 2c, because we know that we're going to have any possible values of d. Okay, so there we go. So that was pretty hasty integration by parts. Give it some practice. So we talked about the indefinite integral. Oh, and I meant to tell you why it's called an indefinite integral. And it's called an indefinite integral precisely because of these c's hanging around, which make it indefinite. It's not something definite because it's a whole family of things. It's not one thing, it's many. It's indefinite. So it's probably not a surprise to realize that there's something called the definite integral. And this is kind of analogous to when you have derivatives. If you take the derivative of a function, you end up with a new function, the derivative function. But you can also evaluate the derivative at a point, and that tells you the slope of the function at a particular point. So in integration, the kind of general thing is to get a family of functions which, when differentiated, give you the original thing. But you can also evaluate the integral. So you're going to find an actual number. I hope that you did the theory for this in a different course, but basically what's happening when you find the definite integral is you're looking at the area under a curve. And the way that you do that is initially by adding up bunches of little rectangles of different widths to estimate the area under the curve. So you can see that if I took the area of, if I took the area of this rectangle and this rectangle and this rectangle, it kind of roughly approximates that area there, and then I'd subtract off this bit, and so on. And as you make your rectangles narrower and narrower and narrower, you get closer and closer to estimating the true area under the curve, where things above the x-axis are positive and things below are negative. And the way that we write this here is, so these are the areas of our little rectangles, because we've got the height, so this is the height of a rectangle at some particular xi star, so there's a height, there's a height, there's a height, and this little delta x is the width. So this term over here gives you the area of the little rectangle that you're using, and then you sum over all the little rectangles, so that's summing over here. And then the final trick, which, as we said, as you make the width narrower and narrower and narrower, you get closer and closer to the approximation. Making the width narrower is the same as having more and more little rectangles. So we let the number of rectangles go to infinity, and we define what we end up with as the definite integral from a to b. So here A is our starting point, our starting value of x, and okay, well, we've got b here. We'd be taking the integral just of this bit over here. So this links a little bit to what I said earlier, that this funny s thing over here is kind of hinting at that sum there. It comes from way back when Leibniz originally talked about derivatives. Okay, this was very hand-wavy, and if you haven't seen it before, I wouldn't stress about it, unless you're particularly interested, in which case go and read some more about it. If you have seen it before, hopefully it jogged your memory, but the key thing that you need to know is, in fact, that you don't need to know this. In the sense that you don't need to be able to take the limit of a sum in order to calculate the definite integral. We're going to use the techniques we've already learnt with the indefinite integral in order to be able to do this. But I just wanted to kind of put this in here because the key thing to take out of this is when you're doing the definite integral, you are thinking about areas under curves, in the same way that when you do the derivative, you're thinking about tangents to curves. Okay, so I promised that you wouldn't have to take the limits of infinite sums, which is delightful. How do we do that? Well, we have what's called the fundamental theorem of calculus, which links together the indefinite integral and antiderivatives and the definite integral. Okay, so suppose we have some continuous function on an interval a to b, and we have our function's antiderivative. So we've got a little f, and we've got its antiderivative, which is big F. Then it turns out that the definite integral from a to b of our little f is the value of our antiderivative at b minus the value of our antiderivative at a. And note that f can be any antiderivative, so you can pick whichever one makes most sense for you. So what this is really saying is that the definite integral of a rate of change of a function is the total change of the function itself on a to b. Maybe read that a few times and think about it, because that emphasizes the link between integration and differentiation. So differentiation is all about finding the rate, and integration is all about, if you're doing the definite integral, it's all about finding the total change of the function. It's undoing all those little rates that you found when you did derivatives. Just a little notation thing. We might often write this f at b minus f at a like so. So if you see that notation, that means take f of x when x is equal to b and subtract it from f of x when x is equal to a prime. There shouldn't be a prime there. Okay, so let's put it all together. Oops, so I need a page. So how do we do this definite integral thing? Well, my advice to you is to first do the indefinite integral and then do the definite integral. There are speedier ways to do it, but if you're anything like me, that leads to bad things happening. So let's first find, so we're going to first find the indefinite integral. So we're going to integrate the integral of x over 1 plus 4x squared dx. Okay, so we have a look at this, and we have a kind of mental checklist we go through. Can we integrate this by I? Maybe you can if you've got a lot of practice, but if you can't, the next thing to think about is, can we do substitution? And here the thing to look at is, do you see a function and its derivative? And there might be factors involved, like constant factors, but that doesn't matter because we can always just divide or multiply as we need to with those. Well, if we have a look at this, notice that in the denominator I've got a 1 plus 4x squared, and if we took the derivative of that, I'd end up with some constant times x. So it certainly looks like this could work for substitution. Let's give it a try. So I'm going to say let u be 1 plus 4x squared. Take the derivative, so du by dx is equal to, well, here I've got an 8x. Now what I really want is just an x times dx. So I multiply through by dx to get du is equal to 8x dx, and I'm going to divide through by 8, because then that will give me that my x dx is 1 over 8 du. And now I make the substitution. So I've got x 1 plus 4x squared dx is equal to, so I'm replacing this with a u, so I've got a 1 over u, and I'm replacing this with a 1 over 8 du. So now we've just got a straightforward integral, integrating 1 over u, which I know is the natural log of the absolute value of u, and I must remember that 1 over 8 plus c. Okay, now don't forget that actually our u involved x's, so we've got 1 over 8 natural log of the absolute value of 1 plus 4x squared plus c. Okay, so it's tempting at this point to breathe that sigh of relief and get on to the next question, but unfortunately we're not there, because our actual question was find the definite integral. But we're really, really close, because what we've found is the antiderivative, or we've found the indefinite integral, but what we actually wanted, if we go back to the notes here, is any antiderivative. So in fact, it's good enough for us to use, I mean, we can use plus c, but we could also just use that as our antiderivative. So that's an antiderivative. And the key thing is that our integral from 1 to 2 of x over 1 plus 4x squared dx is equal to our antiderivative, which I'm going to call big F of x, is equal to our antiderivative at b, which is this upper limit here, minus the antiderivative at the lower limit, which is that bit there. So if you include the c, you'll see that they cancel. So, you know, why would we waste our time including them? Okay, so let's evaluate this thing at 2. I'm going to have 1 over 8 natural log of 1 plus 4 times 2 squared, which is 4. And I'm going to subtract off from that minus 1 over 8 natural log of absolute value of 1 plus 4. Okay, so I've got 1 over 8 natural log of 17 minus 1 over 8 natural log of 5. And if you were feeling super energetic, you could maybe take out a common eighth, and then you'd have natural log of absolute value of 17 minus natural log of 5, and you'd remember your log rules, so you'd end up with the natural log of absolute value of 17 over 15. And then you'd look at that and go, well, we don't really need the absolute values because 17 is positive and 15 is positive. So as a final step, you might want to write, and that shouldn't be a 15, that should be a 5. Sorry, very tired. Okay, but it would have been totally fine if you had stopped at this point. So here we see the key difference between our indefinite and our definite integral. This was our indefinite integral, and it's a family of things. It had a plus c, but our definite integral over here is just a number, which tells us the overall area under this graph between values of x equals 1 and x equals 2. So you can practice B and C, and I'll put the solutions in the final version of this. If you've learned other ways to do this and you're feeling super confident, then by all means go however you feel like it. But if you're still kind of getting up to speed with integration, please do just first find the indefinite integral and then plug in, because otherwise, as I said, bad things can happen. All right, so I just want to give you a brief summary. So remember that the indefinite integral is really a family of functions. And the key thing here is you need to remember the plus c. The definite integral, on the other hand, is just a number. Okay. If we're thinking about in terms of what they mean, the indefinite integral of some function is the family of functions which, when you take the derivative, give you the function that you were interested in. The definite integral, on the other hand, is we're really looking at either area under the graph or the total change of a function between two values. So they have quite different interpretations, but they're linked together by the fundamental theorem of calculus, which was this bunny up here, which told us how to calculate the definite integral using the antiderivatives that we found using in the indefinite integral. Okay, and the final point that I want to make is, we've already talked through this, it's a good idea to have a kind of mental flowchart when you're dealing with integration. How are you going to tackle it? So the first thing is, can you integrate it by eye? If yes, do so, move on with your life. If no, then think about, could you possibly use substitution? So substitution, remember, is undoing the chain rule. So you're going to want to look at a composition where you've got some function embedded within another function and multiplying that, the derivative of the inside function. So here's your inside function, here's its derivative. Obviously, if you spot this and you can do it, then do it, move on with your life. If not, then you're going to use integration by parts. So I used slightly different notation in the lecture, but hopefully you follow that. The key thing for me to try and figure out if I'm going to use integration by parts is that I've got a something multiplied by a something else, and I can't do that integral. So I need to be able to change it around. And so it's really helpful to be able to rewrite it as a new integral plus some term, which I can perhaps do. So my kind of, as I say, my go-to for thinking, should I try parts, is, okay, I've got an integral that has a product, I can't do it using substitution, and I don't know what else to do. Can I transform it into a new integral that I can do? So this was just a little bit more about integration by parts. Of course, there are going to be times when none of that works, and the question is, what do you do there? Well, nowadays, mostly you probably just plug it into Wolfram Alpha to figure it out. There are other integration techniques, but we're not going to cover them here. I think out in the real world nowadays, very few people actually integrate by hand. It's mostly to do with calculators and computers and stuff. But you're probably wondering, so why did we torture you with this? Computers make mistakes. So it is quite useful to be able to check and to really understand what's happening when you get a computer and it tells you this is the integral of something, to be able to look at it and go, does that make sense? Yes, no, because just like humans, weirdly enough, computers make mistakes. Okay, so that was a pretty rushed introduction to, well, I hope not an introduction, I hope a recap for integration. If it was an introduction, I'm sorry, and you should probably go and find a more in-depth thing to read about. So give the examples a go, and also in the tutorial and the exercises, and just make sure that you're feeling comfortable with this. And in the next part of this lecture, we will use what we've developed in the previous part and this part to solve a new kind of equation. All right, see you in a bit. Bye.